In our previous videos for chapter 22, we looked at two different carbon-carbon bond forming reactions based upon the addition of an enolate to a carbonyl. In the first reaction, the aldol reaction, we took two aldehydes, and those two aldehydes could be the same or they could be different, and we said there was a couple strategies that we had to invoke if they were different. But overall, what this did was provide us with a method of making these beta hydroxyaldehydes or ketones. And if we were to heat these up even further after the reaction, we would wind up with an alpha beta unsaturated ketone or aldehyde. The Claisen reaction was very similar in a lot of respects. We still were in the process of generating enolates. They were still reacting with a carbonyl, except now the carbonyl they were reacting with was an ester, which meant that there was a leaving group present, which gave us a way to make these beta keto esters. Okay, and again, both of these are very important types of compounds. They're used extensively in synthesis because they show up so frequently in nature. Now, what we're going to look at today are actually the same exact reactions, except we're going to look at intramolecular versions. And when I say intramolecular, what I'm saying is that we are not going to have two separate aldehydes reacting or two separate ketones or two separate esters. Instead, what we're going to be doing is having a single molecule that contains both of the functional groups that we need for the reactions to take place. So, for example, if we're talking about an intramolecular aldol reaction, that means that we would need to have a compound that has maybe an aldehyde on one end and an aldehyde on the other end. Okay, and this is going to follow all the same principles that we've come to see with these aldol reactions. We're going to add a base, and that base is going to deprotonate one of the alpha protons. Now, in the molecule that I've chosen here, it doesn't really matter which end it attacks. Okay, but what's going to happen here is we're going to remove that alpha proton, and we're going to generate an enolate intermediate. Okay, and I'm just going to draw this in the form of having the negative charge on the carbon still, but we do know that this is going to probably look a lot more like an enolate. And what's going to happen here is we will have that pair of electrons come in and attack the carbonyl on the same molecule. Now, notice what's happened here. We've taken this carbon right here, which is 1, 2, 3, 4, 5, 6 carbons away from the carbonyl. Okay, so we're going to make a 6-membered ring. And I'm going to just arbitrarily number these 1, 2, 3, 4, 5, and 6. That's going to make our lives a lot easier when we're trying to track where everything is. Okay, so we know that the aldehyde has to be coming off of carbon 1. So there's our aldehyde. And we know that carbon 6 was what got attacked, so this is where our hydroxy group is going to show up. Okay, so what we're able to do is make this cyclic structure. And just like we've seen in the other reactions, with any other aldol reaction, if we heat this up enough, we should be able to get this to eliminate to give an alpha beta unsaturated aldehyde, or we can leave it here as the beta hydroxyaldehyde. Okay, this also works with a Claisen reaction. So what I'm going to do here is I'm going to draw up a picture of a diester. Okay, and again, we have these alpha protons that can be removed. So if we treat this with base, we generate the enolate. Okay, and just like before, I'm not going to draw it in the form that has the negative charge on oxygen. I'm going to leave it on the carbon there, but remember that resonance does distribute that negative charge between the carbon and the oxygen. And like we saw before, we are going to have the attack take place on the carbonyl, okay, which is going to break open that pi bond. And like before, let's still number these carbons. Okay, we know that we're going to be forming a 6-membered ring. So like I did before, I'm going to just draw that 6-membered ring, and I'm going to number the carbons. And again, arbitrarily, it doesn't mean that you have to start from the top carbon and go clockwise or anything like that. In fact, just to show that, I'll go and number it like this. So you can see that we can start at a different carbon if we want to. We just need to keep track of which carbon's which. So carbon 1 is going to be the carbon that has the ester on it. Okay, and carbon 6 was the one that got attacked, which means it's the one that's going to have an oxide, a negatively charged oxygen, as well as an ethoxy group. And what winds up happening here is that negative charge can then collapse back down, and we expel the ethoxy group. And what we're left with is a compound that looks like this. Okay, and that provides us with a beta keto cyclic ester. Okay, now the aldol reaction, when it's in its intramolecular form, doesn't really have a special name, but the intramolecular Claisen reaction is known as a Dieckmann cyclization. Okay, now the size of the molecule is what's going to dictate what the size of the ring is going to be. So if we have, let's just stick with the aldol example here. So if we have this dialdehyde that we treat with base, this is the exact same thing that we drew up there before. We're going to wind up with a 6-membered ring. Okay, so this is a 1, 2, 3, 4, 5, 6, 7. That's a 1,7 dialdehyde. Okay, but if we had chosen to use a 1,6 dialdehyde, which would look like this, and treat that with a base, we would wind up with a smaller ring. Okay, just a 5-membered ring. Okay, so we can control the size of the ring by controlling the length of the chain. Now, that being said, trying to make a 4-membered ring this way is not going to be very easy, a lot due to ring strain. 7-membered ring is going to be difficult as well, because we're trying, well, it can happen, but it's going to be more difficult than a six-membered ring. Okay, just generally speaking, five and six-membered rings form fairly easily. Okay, so we can use this for both um, we can use the same strategy for both the Aldol reaction and the Claisen reaction.